All right. Okay, thanks for coming along. My name is Arne Wieberg. I'm from the CERN cloud team, and today I will summarize 5 years of running OpenStack in production in 10 minutes. I've done the math yesterday. That's a compression of 2.5 million to 10. So I will leave out one or the other detail. If you want more details, just grab me afterwards. I'm happy to explain things in more detail. I will start with a quick introduction to what CERN is. So CERN is the European Organization for Nuclear Research. We're doing fundamental research, trying to understand some of the mysteries of the universe. For this, we built the largest machine ever built by mankind, which is the Large Hadron Collider. It's a particle collider built in a tunnel 100 meters underground, 27 kilometers circumference, where particles are accelerated up to almost the speed of light. So they do 11,000 turns per second on these 27 kilometers before they actually collide at 4 interaction points where we have detectors that are like digital cameras trying to understand what happens. Each of these detectors are pretty big. They're pretty heavy, 10,000 tons each. There's like, in each of them, about 1 billion collisions happening per second, which is then going through some trigger hierarchy in order to select the 200 or so events. So you see a picture here of one of the detectors. I don't know if you spotted the physicist already in that picture. He's right there. So this is about the size. It's like cathedral-sized detectors, okay? Now, this is a picture of an event. So these collisions happen, and then these cameras, this detector note what's happening, is collecting all the data. And then the physicists use this data, analyze this data in order to confirm physics theories or to find deviations. And what you see here, the animation is, for instance, this signal that pops up here, which led to the discovery of the Higgs boson a couple of years ago. This analysis is not done at CERN completely. CERN is part of this, provides roughly 20 to 25% of the resources. The analysis is done in a worldwide distributed grid with 170 data centers. We have about 800,000 cores in total, 0.9 or like 900 petabytes of data on disk on tape. And 90% of the CERN resources that are contributed to this are delivered on top of OpenStack. So this is for the CERN introduction. If you want to learn more about what CERN does, about the mysteries, the challenges, the setbacks, the achievements, I invite you to go to our public homepage, home.cern. Now coming to OpenStack, running OpenStack in production, we also had mysteries, challenges, setbacks, and achievements, okay? And I will go through each of them, not each of them, each of the topics now. So let's start with mysteries. So what kind of mysteries do we have in these 5 years? So we had innocent instances being killed randomly. VMs would just disappear, okay? Turns out that this was a random independent service that remembered which PID to kill when to restart, and it just killed VMs here and there. Took us quite a while to identify the murderer. We had hosts that were going down despite being just brought up. So we brought up hosts, and they just shut down. We didn't understand what's happening, but actually it's very bad if you have Ironic, and with IPMI you bypass Nova, and then Nova synchronizes the status, the power status of the host. We had deletions grinding Cinder to a halt, so if you do like mass deletion, like hundreds of volumes in one go, Cinder just stopped for us. And this was because we did in-place upgrades of Cinder, and we carried forward some of the configurations options that we should have updated over the time. We had our bare metal database lose entries, so we enrolled new nodes, they were there, and then after a couple of minutes, they just disappeared from the database, and we didn't understand where these entries were going. Well, it in fact turned out that we mixed up dev and prod, so the dev instance actually could talk to the prod database, said like, okay, I don't know these instances, and they just were removed. So we had upgrades before upgrades. So when we wanted to do the upgrade, we actually realized that the database schema has already been upgraded. Well, some people mix up dev and prod once, we do it twice even. We had no monitoring when doing Manila tests, so I was doing Manila scale tests to see how scalable Manila is with thousands of pods. Actually, that's a very bad idea if you have like 10,000 pods that all try to log something, and then you try to go to the monitoring system, which you just brought down because you log with 10,000 pods. One point I will go into in a little bit more detail is volume or its data loss on reboot. So what we had is, due to the Spectre meltdown vulnerability, we had to reboot the whole cloud, almost 10,000 machines, 35,000 VMs. And there was one user that came back afterwards and said, like, after you rebooted my VM, all my data is gone. Okay? So my first thought was, yeah, it's because probably the volume is not attached or it's not mounted. But actually, the volume was there, it was attached, and it was mounted. So this was a little bit scary because we just did this on 35,000 VMs, okay? Then I looked at FSTop, and at some point I saw this. There's like tempfs. So what the user did is he mounted the volume, he attached the volume, he mounted it, then he wanted to make it persistent. Well, how do you make it persistent? You had a line in FSTop. So he copied a line in FSTop and just changed the source. So he just had the source device changed, but left the type as tempfs. So when I told the user, OK, change this to XFS and reboot, he was very happy that his data was there again. Challenges. So we had a couple of challenges to master when running this service. We have scaled OpenStack to 300,000 cores with almost 40,000 instances now. We use Cells v1 for this, which is like an unsupported method or an unmaintained and unsupported method to support scalability. So this was quite a challenge. We've just moved to v2, which was also quite a challenge. We had to introduce automation and integrate various workflow engines. With the service of that sky, we're doing continuously upgrades. So we have, as you saw on the slide before, like 10 or 12 different OpenStack projects that we run with 2 releases per year. We're basically constantly preparing, doing, or looking at the problems after an upgrade. On top of this, we have to do operating system upgrades. So we're quite good at upgrading everything now. We have to deal with a high team turnover. So the OpenStack team at CERN is like 15 people, so it's this core team of 6 or 7 people, and then we have additional people doing developments, for instance. But over the years, we had like more than 50 people contributing and working in our team. So we have constantly people coming and joining the team and leaving. And so all the knowledge transfer, the training and the knowledge transfer has to be handled. I just mentioned the Spectre meltdown vulnerability. We had to once reboot our whole cloud with all the services that run on it, 35,000 VMs at the moment. One of the larger challenges that we had was we had to fix a virtual to physical performance gap. So what we had here is that we saw on large VMs, so on really large 32 core VMs, we saw in our benchmark a performance loss up to 20%. So we started tuning rather than debugging the performance. So we looked at things at KSM, EPT, pinning, so we could bring it up a little bit. But then at some point, we realized that we compared this with our Hyper-V nodes that we have, and we saw that the issue is actually NUMA awareness. So we did NUMA awareness and no pinning, and we brought it down to something like 3%. And then we rolled it out on our whole batch farm. So this was a huge success. We reduced the virtualization tax from something like 20% on these huge VMs to 3%. But then we also had a setback in the same campaign, because what then happened is that users came back, and after we rolled it out to all these nodes, they said, like, OK, there's like my VM is like super slow, and these were crucial VMs in some of the experiment workflows, blocking the whole experiment, basically. So what this looks like is like the VMs actually looked OK, but the hypervisors had a very high load, and they saw lots of IRQs. Mostly these were TLB shootdowns. So this was a side effect of the fact that we switched off EPT, so extended page table translation in hardware, because these specific applications was relying on, or it was doing a lot of page table walks and needed this support, so it was a very bad idea to switch that actually off. But in our benchmark, switching that off actually helped. So what we went to then is 2 megabyte huge pages to reduce the number of pages that we have, reduce the number of page level translations, and this was a good compromise actually to keep the performance but not run into this issue. But of course, this required a new campaign, so this was really a setback. During these years, we have made quite some good progress. I won't go into detail with this. What I'd like to say is that when it was clear that the way we run IT in CERN in 2012, we could not scale out or scale the operations that we have with the demands that we come from the accelerator. We changed the whole way IT is run at CERN. And OpenStack was one of the cornerstones in this, what we call the Agile Infrastructure project, with the policy that all machines, all services shall be virtualized. Okay? With this, we managed to increase the demand for the resources with the same team size, roughly, that we had before. We reduced the provisioning cycle of resources from months to basically minutes. So rather than waiting for 8 months to get a new physical server for a service, you can boot up a virtual machines in a few minutes. And we established OpenStack as a resource provider interface. It's the only interface where you get all your resources, virtual and physical now. So this, in short, basically enabled the evolution of CERN IT, and OpenStack was the major component that did this. And with this, my 10 minutes are up. Thank you.